All right, question number 12. Using the data from the table below, find the variance and standard deviation for the scores on the quizzes to the nearest tenth of a point. So we're just going to enter this stuff into our calculator. Let's go maybe dual screen so that you can see it a little bit easier. Whoops. So we're going to hit Stat, Edit. We're going to enter this in. Number correct, 1, 2, 3, 4, 5. And then in the other list, we're going to get 1, 2, 5, 5, 12. We go to Calc, one variable statistics, L1, comma, L2. Yeah. So using the data from the table below, find the variance and standard deviations for the scores on the quizzes to the nearest tenth of a point. It doesn't say that we have a sample, right? So which one really should you probably use? Population, right? But I have a feeling in the end it's not going to make a big difference. The only time that really makes a big difference is if it's very obvious that it's a sample or it specifically asks for the sample or the population. Maybe we should do both just to be sure. Yeah? Sx is the standard deviation to the nearest tenth. So that's 1 point what? That's 1.2. And the variance for the sample is equal to 1.2 squared, which is what? 1.44. 1.44. And if you round 1.44 to the nearest tenth, how much is that? 1.4. Now let's see what would have happened also, see if it would have made a difference if we did it for the population. Right? The population standard deviation, what does that get rounded to? 1.2. So what I'm saying to you is it didn't matter either way. The population got rounded to 1.2, so the variance also for the population is going to be what? Yeah, 1.4. That's it. That's all you got to do. Okay. So here we got an electronics company, and they're going to produce headphone sets that can be adjusted to accommodate different size heads. Research into the distance between the top of people's heads and the top of their ears produced the following data, so a whole bunch of numbers. The company decides to design their headphones to accommodate 3 standard deviations from the mean. Find the nearest tenth, the mean, the standard deviation, and the range of differences. So what do we need to do? We need to take that data and plug it into your calculator. We don't need 2 lists this time. We're just going to enter it into one list. Stat, calc, stat, edit. Got to clear out my lists a little bit, so I can work with this. All right, we got. And everybody can see how I'm entering it in. Let me just enter it in without having to record. Okay. So I'm sorry. We plunged the numbers into the calculator. I should show you how we got this. I forgot that I didn't push the record button. We punched the numbers into the calculator. We hit stat, calc. Now normally we hit enter on here and we enter L1 and L2. In this particular instance, all we did was enter numbers into L1. And so we do second L1 and it produces all of our data. And the mean now, everybody knows what all this data is. The mean is 5.5. 5.5. And I'm going to put that in the middle. Okay? To find the mean, the standard deviation, and the range of distances. Well, how much is a standard deviation in this particular case? 0.56. Wait a minute. To the nearest tenth? It's going to be 0.6 because we're using the sample. You know why? Oh, it does though. Find the nearest tenth. It's a good question. So these people are producing electronics for populations, right? They've done research. Look at how many heads they've examined. Have they examined every single person's head? No. They've only examined a sample. So therefore, we use a sample. It's exactly the case. Yes. And so here's the mean, and each standard deviation is worth 0.6. How many standard deviations did we want to go away from the mean? I think we wanted to go 3, right? Do you see what I'm doing here? 3 above, 3 below. Oh, where does it say 3? It says, if you want to read up over here, research into the distances between the top of people's heads and the top of their ears produced the following data. The company decides to design their headphones to accommodate 3 standard deviations from the mean. So 3 standard deviations above for people like me that have enormous size heads and they don't even make hats that fit me. And then people like, you know, maybe my pet who has a really small head and I just might want to put headphones on him to be funny. I don't know. Anyways. So what's 5.5 plus 3.6? Okay. 5.5 plus, yeah, 0.18. No, sorry. Plus 1.8. 7.3, okay. So that's down over here. And then what's 5.5 minus 0.6? 3.7. So yeah, because range is max minus min. Max minus min. What's up? Oh no, in the calculation, it tells you the max minus min of the numbers that you entered in. Yeah. So max minus min, what is 7.3 minus 3.7? Max, the range is 3.6. And we should just indicate that this is the standard deviation. So in a normal distribution, what percent of information falls within 1 standard deviation of the mean? 68. It's just that 68, 95, 99 rule. That's all you had to remember. Let's go to the next one. In a normal distribution, what's the greatest percent of data that falls within 2 standard deviations of the mean? 95. Nice. The mean of a normally distributed set of data is 52. So we're going to stick 52 in the middle. The mean is 52. The standard deviation is 0.4. The standard deviation is 4. Approximately 95% of all cases will lie between which 2 measures? So 95%, what does that ring? What? Yeah, we got to go 2 standard deviations. So you got to go plus 4, and you got to go minus 4, minus 4. So 52 minus 8 is what? 52 plus 8 is 60. That's how you do it. What's up? Yeah. So Professor Bartrich says she's got 184 students in her math class. This is something that you haven't done before. But it's not too bad. The scores on the final examination are normally distributed and have a mean of 72.3. 72.3 is the mean. Goes right in the middle right there. And a standard deviation of 8.9. How many students in the class can be expected to receive a score between 82 and 90? Okay. So let's find out how far up these 2 scores are. Here's our mean. We're going to have to go something to go up over here to get to 82. And then we're going to have to go something more to get to 92. And 90. And what we're really concerned about is this distance right here on the curve. How much do we have to go to get up to be 82? 9.7? Okay. So we had to go 9.7 to get here. Then how much to get from 82 to 90? 8? Okay. All right. So what are we going to do? How much is each standard deviation worth? What's up? Yeah, it's like 8.9. So this is, yeah, this is a weird problem. This is a weird problem. 9.7. This is like plus 1 standard deviation, right? Above it. Let me draw you out the curve for what I'm talking about. Here's our mean. Okay. Here's 72.3. Here's our mean. Here's 72.3. And then here's 82. And then somewhere else down the road, here's 90. We are going to have to find, on the normal distribution curve, approximately this space in between. So this guy right here, 90, is how much above? This is plus 8. So this is like plus 1 standard deviation above, right? So we basically really want to find the space between the first standard deviation and the second standard deviation. Does that make sense? Okay. So now let's go looking on our chart. So Mick, all I did was the following. You see this table over here for normal distribution? Okay. I found that 82 is approximately 1 standard deviation above. You know, it's a little bit more, but we're going to take it for 1 standard deviation above because we don't have a chart that's very precise. The other one, 90, is like 8 more than 82, right? So 90 is like 2 standard deviations above. And what we really want to find is how many students score between 82 and 90. So we want, on your chart, this space right here. Yeah, and that is 9.2% plus 4.4%, which is 13.6%. But it said how many students in the class can be expected to score. So you need to find 13.6% of what? Yeah, 184 students times 13.6% is approximately how many? What's up? Sure you can. You could take a guess at it. 25 out of, that's pretty good. No, you can't. That's why you round down. Let's clear something up here. We got to clear one thing up. When I wrote these numbers underneath, over here, I said I meant that this is approximately 1 standard deviation. Same thing with this one. This is approximately 1 standard deviation. Our hopes in this class are that we come close to stuff. Remember, I told you nothing in statistics is really absolutely perfect. So that's where I got those numbers from. The amount of time that a teenager plays video games in any given week is normally distributed. A teenager plays video games on average 15 hours per week. Is that how much you guys do? Is that low? Okay. Okay. With a standard deviation of 3 hours. So this is a much better problem. This is the same kind of problem, but just with easier numbers. What's the probability of a teenager playing video games between 15 and 18 hours? Well, 15 hours is here, and 18 is above that. 15, I'm sorry. Oh, my God. What am I doing here? 15 is right at the mean. 18 is above that. How much is 18 above that by? By plus 3. Or another way of saying that is by 1 standard deviation above. So you go and look on the bell curve, which you're going to get on your test, and here's what you're going to look for. Right, here's the bell curve. Here's the mean at 15. Here's 18. This is plus 1 SD. And all you want is the area in between. And I think what you're going to find is, when you look on the chart, guess how much that area is? It's like approximately 34%. That's it. Okay, so we're going to finish up 19. 19 is real easy, real easy. We're just going to plug it into our calculator. We want to write a regression, stat, edit. We've got to clear this list, and then we're going to enter prices. So number of blocks from the beach, that's 5, 0, 4, 2, 1, 7. And then the price, 132,000, 310,000, 204,000, 238,000, 275, finally 60,800. And then here's what we're going to do. You go to Stat, Calc, Lin Reg, L1, L2. Enter. And your linear regression is going to be, what do we want that relates to the price of the cottage? Ooh, since it doesn't say where to round, unfortunately, we're going to have to write down that whole number. So it's going to be y equals, oops, negative 34,739. 0.71292 x plus, I'm just going to write it down and come back in a minute. There we go. So that's our linear regression. And then use the equation from part A to predict the price of a cottage to the nearest dollar located 3 blocks from the beach. All we're going to do is plug 3 in for x. Y equals negative 34,739.71292 times 3 plus 31,3309.0909. And so y is going to be equal to, I'm just going to punch that in. And so the price of a home, 3 blocks from the beach, should be something like $210,169, and that makes sense. To the nearest dollar, so that's 210,170. This should be approximately. And let's fix that because it's all messy. I'm sorry, I made a mistake in my calculation. I just accidentally punched the wrong number in here originally. And so actually the answer should be $209,090. $209,090. $1,090. Sorry about that. Sorry about that. Last problem, we're going to do the same thing, except we're just going to do a power regression this time. We're going to enter stuff into the calculator. Stat, edit, we're going to clear out our lists. We're going to enter in 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just going to enter this in. You don't need to watch me for spam. All right, so we're going to do this. We're going to enter it in, and then we're going to do a power regression calc. Scroll down until you find the one that you want, power regression, on L1, L2. Rounding all constants to 3 decimal places. There we go. So we're going to do y equals. So that's what you should get from there. 274. And then, so that's part A. And then, what will the average monthly payment be in 15 years to the nearest cent? All we're going to plug in is 15 for x, and then we're going to be done. So y should be 539, 274 times 15 raised to the 0.0142. Let's throw it in the calculator. And it is approximately $792.162. To the nearest cent. Sorry about that. So the nearest cent is 792.16 cents.